Pick up anything near you, a pencil, a coffee cup, your own hand. It feels solid, right? It feels like a thing. Like it is made of smaller things, atoms. And those atoms are made of even smaller things, electrons and protons and neutrons, little balls, little marbles rattling around inside a bigger marble. That is the picture most people carry in their heads. And I am here to tell you tonight that picture is wrong. Completely, beautifully, spectacularly wrong. There are no particles. Not really. Not in the way you think. You are not made of things. You are made of fields. And by the time we are finished here, you will understand what that means, why it matters, and why, frankly, it is one of the most astonishing facts about the universe that hardly anybody talks about. So let us start where any sensible person should start, which is with something you already know. You know what a wave is. You have seen waves at the beach. You stand there, the water comes in, the water goes out. Now here is the important question. When a wave moves across the ocean, does any water actually travel from out there to the shore? No. The water just goes up and down. The wave is not a thing that moves. The wave is a pattern that moves through the water. The water is the medium. The wave is just a disturbance, a ripple, a shape passing through. Now keep that in your mind. Hold it, because it is the key to everything. Let us go back to the old days. The ancient Greeks had this lovely idea. They said, look, if you take a piece of cheese and you cut it in half, and you cut it in half again, and you keep cutting, eventually you get to something you cannot cut anymore. They called it atomos, indivisible. And for a long time, that seemed like a perfectly good idea. Matter is made of tiny, indivisible balls, little pellets, little grains of sand that are too small to see. Then along comes the electron, discovered by J. Thomson in 1897, a tiny charged particle inside the atom. Then Rutherford finds the nucleus, a hard little kernel at the center. And suddenly everybody has got this solar system model of the atom, electrons orbiting a nucleus like planets around the sun. And it is a gorgeous picture. Simple, clean, wrong. See, the trouble started almost immediately. If an electron is really a little ball orbiting the nucleus, then according to everything we knew about electricity and magnetism, it should be radiating energy. It should spiral inward and crash into the nucleus in about 100 millionth of a second. Every atom in the universe should have collapsed long ago. You should not be sitting there. I should not be standing here. And yet here we are. So something is terribly wrong with the little ball picture. Now, around 1925, 1926, some very clever people, Heisenberg, Schrödinger, Dirac, they figured out something new. They gave us quantum mechanics. And quantum mechanics tells you that an electron does not have a definite position until you measure it. It is described by a wave function, a spread out mathematical object that gives you the probability of finding the electron here or there or over there. Already the little marble is getting fuzzy. It is not really in one place. It is sort of everywhere at once, in a certain sense, until you look at it. But even quantum mechanics, as marvelous as it was not the final word, because quantum mechanics still treated particles as fundamental objects. It said, okay, the electron is not a classical ball, it is a quantum object described by a wave function, but it is still a thing, it is still an electron, a single entity. And then came the real revolution, quantum field theory. And this is the thing that most people, even most people who took a physics course, never quite heard about. And it changes everything. Here is the idea. Forget particles. Forget little balls. Forget little fuzzy balls. Instead, imagine that filling all of space, everywhere, in every direction, as far as you can go, there is a field. What is a field? A field is just a quantity that has a value at every point in space. Temperature is a field, in a sense. At every point in this room, there is a temperature. It might be 70 degrees here and 72 degrees over there and 68 degrees by the door. That is a field, a number at every point. Now, the universe is filled with fields. There is an electron field that permeates all of space. There is a quark field. There is an electromagnetic field, which you already know about from light and radio waves. There is a field for every type of fundamental entity we have ever discovered. These fields are always there. They fill the whole universe. They never go away. And here comes the punchline. What we call a particle, an electron, a photon, a quark, is not a thing. It is a vibration in one of these fields. It is a ripple. It is an excitation. Remember the ocean wave? The wave is not a thing. It is a disturbance in the water. An electron is not a thing. It is a disturbance in the electron field. Now wait, let that land for a second, because this is not just a different way of talking about the same thing. This is a completely different picture of reality. In the old picture, you have empty space, and in that empty space, there are particles flying around, bumping into each other. Space is the stage, particles are the actors. In the new picture, the fields are the stage and the actors. There are no particles flying through empty space. There are only fields vibrating. When a field vibrates a little bit, we call that vibration a particle. When it stops vibrating, the particle is gone. The field is still there. It is always there. But the excitation, the little bundle of energy we called a particle that can appear and disappear. Let me give you another analogy. Think of a wheat field on a windy day. You know what happens. The wind blows and you see waves rippling across the top of the wheat. Beautiful, right? Now, those waves are real. You can see them. You could even photograph them. But is there a thing called a wheat wave that exists independently of the wheat? No. The wave is just the wheat moving. If you take away the wheat, there is no wave. The wave is what the wheat does when it is disturbed. That is exactly what an electron is. The electron field is the wheat. The electron, the thing we detect in our experiments, is the wave. Take away the field, there is no electron. The electron is what the electron field does when it is excited. Now, I want to be careful here, because people sometimes hear this and they say, oh, so particles are just illusions? They are not real? No, no, no. The excitations are real. When you detect an electron, you detect something real. Energy is really transferred. Momentum is really transferred. It is just that the thing you detected is not a little marble. It is a quantized excitation of a field. The wave has a definite minimum size, a quantum, and that quantum is what we call the particle. This is what the word quantum really means, by the way. It means that the vibrations of the field come in discrete lumps. You cannot have half an electron. You cannot have 3/4 of a photon. The field can vibrate, but only in whole number units. 1 excitation, 2 excitations, 3 excitations, never 1.5. That discreteness, that lumpiness, is where the word quantum comes from. And it is why, when we do experiments, it looks like particles. The energy arrives in lumps, but the underlying reality is the field. Let me do a Feynman check here. Let me make sure we are all together. Imagine I am explaining this to a bright kid, about 12 years old. I would say it like this. You know how a guitar string can vibrate? When you pluck it, you get a note. The string vibrates, and we hear a sound. Now imagine a guitar string that fills the entire universe, not just stretching across a guitar, but going everywhere, through every point in space. When that string vibrates a little bit in one spot, that vibration is what we call a particle. The string is the field. The vibration is the particle. And the universe has many such strings, one for each type of particle. There is a string for electrons, a string for photons, a string for quarks, and All of what we call matter and energy is just these cosmic strings vibrating. That is the simplified version, but it captures the essential truth. Reality is fields. Particles are what fields do. Now, here is a common misconception I want to deal with. A lot of people, even some physicists, when they're being sloppy, will say something like this. They will say, well, sometimes an electron behaves like a particle, and sometimes it behaves like a wave. It depends on the experiment. This is called wave-particle duality, and it is one of the great mysteries of quantum mechanics. But here is the thing. If you take quantum field theory seriously, there is no mystery. There is no duality. The electron field is always a field. It is always wave-like at the fundamental level. But the field is quantized. Its excitations come in lumps. And those lumps behave in certain experiments like little localized things. So when you shoot electrons at a detector one at a time, each one lands at a specific point. Click, like a particle. But if you run the experiment many times, the pattern of clicks builds up into an interference pattern, like a wave. There is no switching back and forth. The field is doing exactly the same thing every time. The confusion comes from trying to force the field into one of two classical categories, wave or particle, when really it is neither. It is a quantum field, something new, something that has no perfect analogy in everyday experience. When we say particle, we mean a quantized excitation. When we say wave, we mean the field itself, spreading and interfering. Same thing, two different aspects. No mystery, no duality. Just a quantum field doing what quantum fields do. Now let me tell you something absolutely wonderful that falls right out of this picture. Something that, if you think about it the old way with particles, seems like the most incredible coincidence. But in the field picture, it is completely obvious. Every electron in the universe is identical. Every single one. Not just similar, not just really, really alike. Identical. The electron in your left eye has exactly the same mass, exactly the same charge, exactly the same magnetic moment as the electron in a star 10 billion light years away. In the entire history of the universe, no one has ever found an electron that is even slightly different from any other electron. They are all exactly the same. Now, if electrons were little marbles, this would be the most astonishing coincidence imaginable. Why should all the marbles be the same? Who manufactured them? Where is the factory? Did someone stamp them all out of the same mold? It makes no sense. But in the field picture, it is trivially obvious. All electrons are the same because they are all excitations of the same field. They have to be the same. It would be like asking why all the waves in the ocean are made of water. Well, because they are all disturbances in the same ocean. All electrons are identical because they are all ripples in the same electron field. There is only one electron field in the entire universe, and every electron is a vibration of that one field. Of course, they are all the same. This is not a small thing. This is a profound insight. The identity of particles, which in the old picture is a brute, unexplained fact, becomes in the field picture a trivial, automatic consequence. Now I want to take you on a thought experiment. I want you to imagine empty space, really empty. No atoms, no light, no radiation, no nothing. Just a perfect vacuum. According to the old particle picture, empty space is empty. There is nothing there. Just a big, black, quiet void. But according to quantum field theory, empty space is not empty at all. The fields are still there. The electron field is still there. The quark field is still there. The electromagnetic field is still there. Every field is still there, filling all of space, even when there are no particles. And here is where it gets really interesting. These fields cannot be perfectly still. That is the thing. Quantum mechanics has this rule called the uncertainty principle. And one version of it says that you cannot simultaneously know the value of a field and how fast that value is changing with perfect precision. So even in the lowest possible energy state, the so-called vacuum state, the fields are still jiggling. They're still fluctuating, just a tiny, tiny bit. These fluctuations are called vacuum fluctuations, or sometimes zero-point fluctuations. And they are real. They have measurable consequences. Let me give you one. In 1948, a Dutch physicist named Hendrik Casimir predicted something remarkable. He said, take two uncharged metal plates and put them very close together in a vacuum. There should be a tiny force pushing them together. Not gravity, not electrostatics, something new. A force that comes purely from the vacuum fluctuations of the electromagnetic field. And it was measured. It took a while, but it was measured, and Casimir was right. The force is there. The vacuum, the so-called empty space, is pushing those plates together. Empty space is not empty. It is fizzing and bubbling with field fluctuations at every point, all the time. Now, people sometimes talk about virtual particles in this context. They say the vacuum is full of virtual particles, little particle-antiparticle pairs popping in and out of existence. And you have to be careful here, because the language of virtual particles is useful for doing calculations, but it can be misleading about what is actually happening. What is really happening is this. The field is fluctuating. The quantum field has a minimum energy, even in its ground state, and that minimum energy is not zero. It is not that particles are literally popping into existence and then disappearing. That is a dramatic story, and it is based on a certain way of drawing Feynman diagrams, but it is not quite what the math says. What the math says is that the field has quantum uncertainty in its ground state, and that uncertainty has physical consequences. The Casimir effect is one of them. The Lamb shift, a tiny change in the energy levels of hydrogen, is another. So let us be honest about what we know and what is interpretation. The fields are real. The fluctuations are real in the sense that they have measurable effects. The language of virtual particles is a convenient bookkeeping device for calculations. Whether you want to say virtual particles are real depends on what you mean by real, and that gets into philosophy, which is interesting, but let us not get lost in it. Let me tell you now about how particles interact. In the old picture, you might imagine two electrons approaching each other, and at some point they feel each other's electric field and push apart. That is fine for a rough picture, but in quantum field theory, the interaction works differently, and it is beautiful. Here is what happens. One electron, which is an excitation of the electron field, disturbs the electromagnetic field. It creates an excitation in the electromagnetic field. That excitation travels across to the other electron and disturbs it. The two electrons have exchanged energy and momentum through the electromagnetic field. Now, that excitation of the electromagnetic field, the one that carried the interaction, that is what we call a virtual photon. It is not a real photon. You cannot catch it with a detector. It does not have to obey the usual rules about energy and momentum the way real photons do. It is an intermediate disturbance, a middleman. But through this mechanism, the two electron field excitations push each other apart. And this is how all forces work in quantum field theory. Every force is mediated by a field. Electromagnetism is mediated by the electromagnetic field, whose quanta are photons. The strong nuclear force is mediated by the gluon field. The weak nuclear force is mediated by the W and Z fields. Even gravity, if we ever figure out how to quantize it properly, would presumably be mediated by the gravitational field, whose quantum we call the graviton. So the picture is this. The universe is not made of particles bouncing around in empty space. The universe is a collection of quantum fields overlapping and interacting, filling all of space and time. What we call particles are just the quantized excitations of these fields. What we call forces are just the ways these fields influence each other. Now let me tell you about one more field. because it is important and because it is the one that took the longest to confirm. The Higgs field. You may have heard about the Higgs boson. There was a lot of excitement when it was discovered. But the boson is just the quantum of the Higgs field, just like a photon is the quantum of the electromagnetic field. The real story is the field itself. The Higgs field is different from the other fields in a crucial way. Most fields, in their lowest energy state, have a value of 0. The electromagnetic field, when there are no photons around, has 0 value. It is calm. It is quiet. But the Higgs field, in its lowest energy state, does not have a value of 0. It has a non-zero value everywhere. It fills all of space with a constant, non-zero background value. And this background value is what gives mass to certain particles. When an excitation of the electron field tries to move through the Higgs field, it interacts with that non-zero background. That interaction slows it down, in a sense. It makes it harder to accelerate. And that resistance to acceleration is exactly what we mean by mass. The electron has mass because it interacts with the Higgs field. The quarks have mass for the same reason. The photon does not interact with the Higgs field, and that is why the photon is massless. It is a remarkable idea. Mass is not an intrinsic property of a particle. Mass comes from the interaction between one field and another. Without the Higgs field, electrons would zip around at the speed of light, like photons. There would be no atoms, no chemistry, no you, no me. The Higgs field is not just another field. It is the field that makes the universe as we know it possible. Now I want to step back and talk about something that might be bothering you. If everything is fields, if there are no particles, then what about me? What about you? What about this table? What about the whole solid, tangible world we experience every day? Well, here is the thing. The solidity you feel when you touch a table is not because atoms are solid balls. Atoms are mostly empty space, even in the old picture. What makes the table feel solid is the electromagnetic force between the electron fields in your hand and the electron fields in the table. Those fields resist being pushed into each other. The Pauli exclusion principle, which says that no two electrons can occupy the same quantum state, means that the electron fields in the table push back against the electron fields in your hand. That pushing is what you feel as solidity. So even your everyday experience of solid matter is really an experience of fields interacting. You have never touched a particle. You have only ever felt one field pushing against another field. Let me go even further. Every sensation you have ever had is a field phenomena. Light enters your eye. What is light? An excitation of the electromagnetic field. It hits the molecules in your retina. What are those molecules? Patterns of excitations in electron fields and quark fields held together by the electromagnetic field and the strong nuclear field. A chemical reaction occurs. That reaction is a rearrangement of field excitations. An electrical signal travels along your nerve. That signal is a moving pattern of field excitations. Your brain processes the signal. Your brain is a collection of field excitations processing other field excitations. You have never experienced anything other than quantum fields. Your entire life, from your first breath to this very moment, has been an experience of quantum fields interacting with quantum fields. Now, I know what some of you might be thinking. You might be thinking, okay, Feynman, this is all very poetic, but is it really true? I mean, can we really be sure that there are no particles? Maybe particles are real and the fields are just a mathematical trick. That is a fair question. And the honest answer is that quantum field theory is the most precisely tested theory in the history of science. The predicted value of something called the anomalous magnetic moment of the electron, which is a measure of how an electron interacts with a magnetic field, agrees with experiment to about 12 decimal places. 12. That is like predicting the distance from New York to Los Angeles to within the thickness of a human hair. No other theory in any branch of science has ever been confirmed to that level of precision. And the theory that gives you that prediction is quantum field theory, not classical particles, not quantum mechanics with little balls. Quantum field theory, with its fields filling all of space and its quantized excitations that we call particles. That is the theory that works. That is the theory that matches what we actually observe in the laboratory. Now, does this mean that quantum field theory is the final word? Of course not. We know it cannot be, because we have not been able to reconcile it with general relativity, with Einstein's theory of gravity. At very small distances, near the Planck scale, something new must happen. Maybe the fields themselves are made of something deeper. Maybe space and time are made of something deeper. We do not know. That is one of the great open problems. But within its domain, which covers everything from the behavior of individual electrons to the structure of nuclei to the radiation from stars, quantum field theory is unmatched. It is the best description we have of how the universe actually works at the fundamental level. Let me tell you something else that comes out of the field picture, something deep and strange and wonderful. It has to do with antimatter. In 1928, Paul Dirac wrote down an equation that combined quantum mechanics with special relativity to describe the electron. And when he solved his equation, he found something unexpected. The equation had two kinds of solutions. One kind described the electron as we know it, with negative charge and positive energy. The other kind seemed to describe an electron with positive charge, an anti-electron, a positron. Dirac had predicted the existence of antimatter from pure mathematics. And a few years later, in 1932, Carl Anderson found the positron in cosmic ray experiments. It was there, exactly as Dirac predicted. But in the field picture, antimatter is not mysterious at all. Remember, the electron field can have excitations. A positive energy excitation is what we call an electron. But the field can also be excited in a different way, and that different kind of excitation is what we call a positron. Same field, different excitation. Electron and positron are two different ways the electron field can vibrate. And when an electron meets a positron, they annihilate. They both disappear, and their energy goes into the electromagnetic field as photons. In the field language, what happened is that the excitation and the anti-excitation of the electron field canceled each other out, and the energy was transferred to the electromagnetic field as a pair of excitations. Vibrations canceling in one field, exciting another. Fields talking to fields. That is all it is. Now here is something else that falls naturally out of the field picture, something that sounds absolutely crazy in the particle picture, but is perfectly sensible when you think in terms of fields. In quantum field theory, the number of particles is not fixed. Let me say that again. The number of particles in the universe is not a fixed number. In the old picture, you have some number of electrons, some number of protons, and they just rearrange themselves. The total count stays the same. But that is not what happens when an energetic photon, a gamma ray, passes near a nucleus. It can disappear, and in its place, an electron and a positron can appear. One photon goes in, two particles come out. The number went up. How do you explain that if particles are fundamental things? Where did the new particles come from? Were they hiding somewhere? That makes no sense. But in the field picture, it is perfectly clear. The electromagnetic field was excited. That excitation, the photon, carried a certain amount of energy. That energy was transferred to the electron field. And the electron field used that energy to create two excitations, one electron and one positron. Nothing was hiding. Nothing appeared from nowhere. Energy moved from one field to another, and the second field used that energy to vibrate in two new spots. Fields can do that. They can accept energy and create new excitations. This is called pair production, and it happens all the time. Cosmic rays smashing into the atmosphere produce showers of new particles. Particle accelerators create new particles by pumping energy into the fields. In every case, what is happening is energy being transferred from field to field, with new excitations appearing and old ones disappearing. And here is the thing. In the particle picture, you need special rules to explain this. You need conservation laws, creation operators, annihilation operators. It all feels very ad hoc, like you are bolting on extra machinery. But in the field picture, it is just what fields do. Fields fluctuate. Fields exchange energy. New excitations appear. Old ones vanish. It is as natural as waves on the ocean. Sometimes two waves merge into one big wave. Sometimes one big wave splits into two smaller waves. Nobody finds that mysterious. It is just what waves do. And that is all that particle creation and annihilation is. It is just what quantum fields do. Let me talk now about the Standard Model, because this is the thing that puts the whole picture together. When physicists talk about the Standard Model of particle physics, what they really mean is a specific quantum field theory. It is a theory that says, here are all the fields we know about, and here are the rules for how they interact. And how many fields are there? Not that many, actually. There are 6 quark fields: up, down, charm, strange, top, and bottom. There are 3 charged lepton fields: electron, muon, and tau. There are 3 neutrino fields, 1 for each charged lepton. There are the force-carrying fields: the electromagnetic field, the gluon fields for the strong force, and the W and Z fields for the weak force. And there is the Higgs field. That is it. Around 17 or so fields, depending on how you count, plus their interactions. And from those 17 fields and few dozen numbers, the coupling constants and masses, you can derive everything: the structure of atoms, the behavior of light, the nuclear reactions that power the sun, the reason why the sky is blue and the grass is green and gold is gold-colored, all of chemistry, all of nuclear physics, all of the interactions of matter and energy that we have ever observed in any laboratory experiment, ever. It is an extraordinary achievement. It is, as far as we can tell, a correct description of everything that happens in the physical world, with 2 exceptions. It does not include gravity in a quantum way, and it does not account for dark matter and dark energy, whatever those turn out to be. But for everything else, for the entire zoo of physical phenomena that human beings encounter in laboratories and in daily life, the Standard Model, this one quantum field theory, gets it right. And remember, the Standard Model is not a theory of particles. It is a theory of fields. The particles show up as a consequence. They are the excitations, the quanta, the lumps. But the fundamental description is all about fields and their interactions. That is what the equations describe. That is what the theory is about. Now, let me say a word about something called renormalization, because I think it tells you something important about the nature of quantum fields and about the honesty of physics. When you try to calculate things in quantum field theory, you often run into a problem. The calculations give you infinity, not a big number, infinity. For example, if you try to calculate the self-energy of an electron, the energy the electron has due to its own electromagnetic field, the answer comes out infinite. That is, shall we say, not a very useful answer. Now, for a while, this drove people crazy. They thought the theory was broken, but then some clever people, Tomonaga, Schwinger, and, well, yours truly, figured out a procedure called renormalization. The idea is that the infinities can be absorbed into the quantities we actually measure, like the mass and charge of the electron. You redefine the mass and charge to include the infinite corrections, and then all the other calculations give you finite, sensible answers, very precise, very accurate answers. Now, is renormalization a trick? Some people thought so. Some people thought we were sweeping the infinities under the rug. And I had my own doubts about it, I will be honest. But the answers it gives are correct. They match experiment to extraordinary precision. And over the years, people have come to understand renormalization not as a trick, but as a deep feature of quantum field theory. The infinities arise because we are being naive about what happens at very short distances, at very high energies, where we do not really know the physics. Renormalization is a way of saying, look, I do not know what happens at those extreme scales, but I can still make precise predictions about what happens at the scales I can actually measure. And it works. It works so well, in fact, that quantum electrodynamics, the quantum field theory of electrons and photons, gives you that 12 decimal place agreement I mentioned earlier. That is renormalization doing its job. Now, I want to address one more thing before I bring this all together. People sometimes ask, what is the field made of? If particles are excitations of the field, what is the field made of? And the answer, as far as we know, is nothing. The field is not made of anything more fundamental. The field is the fundamental thing. It is not made of little atoms of field. It is not a substance in the way we usually think of substances. It is a quantum field, which is a mathematical object with certain properties, and it is the most basic level of description we have for the physical world. Now, that might feel unsatisfying. You want to know what it really is. You want to peel back one more layer. And I understand that impulse. I have it too. But at some point, you reach the bottom of the stack. You reach the level where the description just is what it is, and there is nothing underneath. And the quantum fields might be that level, or maybe not. Maybe there is something deeper. But right now, the quantum fields are where we are. They are the bedrock. Let me take you through one more beautiful thing. I mentioned Feynman diagrams, and since they have my name on them, I suppose I should say a few words. When we want to calculate what happens when two fields interact, when two electrons scatter off each other, or when an electron emits a photon, we can draw little pictures. Lines for the particles, vertices where they meet. These are Feynman diagrams, and they are not just pretty pictures. Each diagram corresponds to a precise mathematical expression. You draw the diagram, you write down the integral, you compute the number. But here is the thing people often get wrong. The diagrams are calculational tools. They are not pictures of what is happening in space. When you draw a line in a Feynman diagram, it does not mean a particle is literally traveling along that line through space. The diagram is a shorthand for a very complicated integral over all possible field configurations. It is a way of organizing the mathematics. This is important because sometimes people look at Feynman diagrams and they say, look, there is a particle going from here to there, and here it emits a photon, and there the photon is absorbed, and they think that is what is physically happening. But that is just one picture, one contribution to the full calculation. The full answer involves summing over all possible diagrams, including diagrams that look very strange if you try to think of them as literal pictures of particles traveling through space. The diagrams work because the underlying theory is a field theory. They are a clever way of computing what the fields do. But they can trick you into thinking that particles are more fundamental than they are if you are not careful. Now, let me bring all of this together. What is the picture of reality that quantum field theory gives us? The universe, at its most fundamental level, is not made of particles. It is not made of tiny billiard balls or little hard spheres or even tiny fuzzy quantum blobs. It is made of fields. Quantum fields filling all of space, always present, always fluctuating, always interacting. What we call an electron is a quantized excitation of the electron field. What we call a photon is a quantized excitation of the electromagnetic field. What we call a quark is a quantized excitation of the quark field. And so on for every fundamental entity in nature. These fields interact with each other. The electron field interacts with the electromagnetic field, and that is how electrons emit and absorb light. The quark field interacts with the gluon field, and that is how the strong nuclear force works. The electron field interacts with the Higgs field, and that is how the electron gets its mass. Out of these interactions come atoms. Out of atoms come molecules. Out of molecules come cells. Out of cells come you and me. All of it, from the smallest quark to the largest galaxy, is just quantum fields vibrating. Think about that for a moment. The hand you are looking at right now is not made of stuff. It is made of patterns. Patterns in fields. Stable, persistent, beautifully organized patterns, but patterns nonetheless. You are not a collection of things. You are a symphony of fields. And the remarkable thing, the thing that gets me every time I think about it, is that these fields are governed by relatively simple rules. The equations of quantum field theory, while difficult to solve, are not themselves complicated. A handful of fields, a handful of interactions, and out of that comes everything. Every color you have ever seen, every sound you have ever heard, every thought you have ever had, all of it, from the simplest hydrogen atom to the most complex structure in the known universe, which is the brain you are using to understand this sentence right now, all of it is quantum fields interacting according to these rules. Now, I want to say something about what this means for how we think about the world, because I think it matters. It matters not just for physics, but for how we understand our place in the universe. In the old picture, the universe is made of stuff, little hard things bouncing around, and you are made of that same stuff. You are a machine built from parts, like a watch. There is something a bit cold about that picture. In the field picture, the universe is not made of stuff. It is made of processes. Everything is a field excitation, and field excitations are dynamic. They are happenings, not things. An electron is not a little ball sitting there. It is a vibration, a process, an event, and you are not a static thing either. You are a pattern of processes, a standing wave in the quantum fields of the universe. You are something the universe is doing right now, here, in this particular configuration. I find that picture more beautiful, more honest, and more humble, because in the field picture, there is no sharp boundary between you and the rest of the universe. The fields that make up your body are the same fields that make up the air around you, the floor beneath you, the stars above you. The boundaries are patterns of excitation, not walls between different kinds of stuff. At the deepest level, it is all one thing, one set of fields, vibrating, and we are the parts of the vibration that woke up and started asking questions about the vibration, which, when you think about it, is pretty remarkable. Now let me take you through one more thought experiment, because I think it really drives the point home. Imagine you have a box, a perfect sealed box. Inside the box is a single electron. In the old picture, there is a little ball bouncing around inside the box. It hits the walls, it bounces back, it hits the other wall. Simple. But in the field picture, what is inside the box? The electron field is inside the box. In fact, the electron field was already inside the box before you put the electron in. The electron field fills all of space, including the inside of the box. What you did when you put an electron in the box was you added one quantum of excitation to the electron field inside the box. You raised the vibration level by 1 unit. Now here's where it gets strange. That excitation is not in one place inside the box. The wave function of the electron spreads out to fill the box. There is some probability of detecting the electron here, some probability of detecting it there. The excitation is delocalized. It is everywhere inside the box at once. And here is the really strange part. Suppose you make the box smaller. You squeeze it. What happens? The excitation has less room. And because of the uncertainty principle, confining the field to a smaller region means the momentum becomes more uncertain, which means the energy goes up. The more you squeeze, the more energetic the excitation becomes. At some point, if you squeeze hard enough, the energy becomes so large that the electron field can create new excitations. You started with one electron, and by squeezing the box, you can end up with an electron, a positron, and another electron. 3 excitations where you started with one. The energy you put in by squeezing became new particles. This is not science fiction. This is what actually happens at particle accelerators. You squeeze things together, you pump in energy, and new excitations pop out of the fields. New particles, as we call them. But really it is just the fields accepting energy and vibrating in new ways. And this tells you something deep. Particles are not permanent. They are not eternal. They are not indestructible building blocks. They are temporary patterns of excitation. They can be created, they can be destroyed. They can transform from one kind into another. The only things that persist, the only things that endure, are the fields themselves. You know, people sometimes talk about the conservation of matter. Matter can neither be created nor destroyed, they say. But that is not quite right. What is conserved is not matter. What is conserved is certain quantities, like energy and electric charge and baryon number. The excitations themselves come and go. An electron and a positron can annihilate and become 2 photons. The electron is gone, the positron is gone, but the energy is still there, in the photon field now. And the total charge is still 0, because the electron had charge -1 and the positron had charge +1. The conservation laws hold, but the particles are gone. So if you want to know what is permanent in the universe, it is not particles, it is not matter, it is the fields and the symmetries that govern them. Now, I have been going on for a while, and I want to make sure I have not left anything fuzzy. So let me say the main point one more time, as clearly as I can. The particles you learned about in school, electrons, protons, photons, all of them are not fundamental objects. They are not the building blocks of reality. The building blocks, if you want to call them that, are quantum fields. And what we call particles are just the way those fields vibrate. Every particle is a ripple. Every force is a field interaction. Everything you have ever seen or touched or known is a pattern of vibrations in quantum fields. That is the universe. That is what physics has discovered. And I think it is one of the most magnificent things human beings have ever figured out. So here is what I want to leave you with. The next time you look at your hand, or a flower, or the night sky, remember what you are really looking at. You are looking at quantum fields, fields that have been vibrating since the beginning of the universe, fields that will go on vibrating long after you and I are gone. And for this brief, extraordinary moment, some of those vibrations have arranged themselves into a pattern that can look at the stars and wonder what they are made of. That is you, a wondering vibration. I cannot think of anything more wonderful than that. Now, if you have made it this far, I would be delighted to know what you think. Here is a question for you. If everything is really made of fields and not particles, does that change how you think about yourself? Does it change what it means to be a thing? Write your answer below and let us have a conversation about it.